we are going to use the log base b of b equals 1. Remember, we had those properties. And we also know that the log base b of 1 equals 0. I already have 2 points. Now, the other thing that you do need to know about logs, if our exponential function looks like this, where we always have this horizontal asymptote at y equals 0, and my graph always goes through the point 0, 1. This is my exponential function. This is b to the x. My log function, if you remember what inverse functions do, is they reflect around this y equal x line. Let's put a y equal x line here. If the domain and range switch, that means I'm always going to have a point here at 1, 0. And if I have an asymptote here at y equals 0, guess what? I'm going to have an asymptote at x equals 0 for the log function. Notice as x gets smaller and smaller, y goes to 0. I have to reverse that. As y gets smaller and smaller, x goes to 0. And then if I reflect it over that y equal x line, it would look like this, which is the basic shape of the log base something of x. We can see that they reflect over this x equal y line. We know that we have this vertical asymptote now at x equals 0. As I said before, we always go through this point 1, 0. B of x equals y. We also have this point here. So when x equals 3 is the log base 3 of 3, which is up here, equals 1. So if I plot my other point, this is 3, y is going to be 1. And from there, I can actually just graph it. I know that as I get closer and closer to this asymptote, it's going more and more negative. And as I get further and further out, it is going to rise, but it's going to rise pretty slowly, as opposed to the exponential function, which rises very quickly. If I have 2 points, here's what they wanted. And they created this exponential function. We flip the domain and range. Of course, we get that 0.10. And of course, we're going to still get that 0.31 that we used. But we can get as many points as we want now, because there's also a point at 1/3 -1. Let's pretend that's 1/3 -1. Our graph is going to look like that, reflecting over the y equal x line. Whichever way you like better, use that. Remember, the log function rises slowly. It's this red one. The exponential function rises very quickly. It's the blue one. Characteristics of logarithmic functions. For b is greater than 0, and of course b can't be 1, the logarithmic function with base b is defined by y equals log base b of x. The domain of log base b of x is from 0 to infinity. We saw that from the graph. There is a vertical asymptote right here. It can't go through a vertical asymptote. The smaller x gets, or the closer x gets to 0, the more negative it will become, because it's following that asymptote. And the range, you can see, is going from negative infinity to positive infinity. It goes all the way down to negative infinity, and it keeps rising here up to positive infinity. The graph intersects the x-axis at 1, 0. The graph contains the point b, 1 and 1 over b, negative 1. If I have log base b of b, we already know that property is b equals 1. If I have the log base b of 1 over b, that's the same as the log base b of b to the minus 1 power. 1 over b equals b to the minus 1 power. Again, using the cancellation property, this equals negative 1. The graph is increasing from 0 to infinity. The y-axis, or x equals 0, is our vertical asymptote. And again, the function is 1 to 1. When b is between 0 and 1, it flips over at the x-axis. And it still goes through the point 1, 0, but it's decreasing. This being the log base b of x, when b is between 0 and 1, it flips over the x-axis. And the graph is decreasing on that interval. It still has the same vertical asymptote, and it's still a 1-to-1 function. But now, instead of increasing, it's decreasing if the base is between 0 and 1. Finding the domain of any log function, that argument has to be greater than 0. The domain log base 5 of x is going to be 0 to infinity. That's always true. Now, what happens if we have the log base 5 of negative x? Well, we have to start with negative x has got to be greater than 0. How do we solve for x? Well, remember, we can either multiply or divide by negative 1, which means this becomes x, and this is still 0. But remember, when I multiply or divide by a negative number, I flip the inequality sign. I divided by a negative 1, which means I flip the inequality sign. Now what this is saying is x can only be negative, which should make sense because when I plug in a positive value for x, this becomes negative, and I can't take the log of a negative number. However, if I plug in a negative number, then negative becomes positive, and I can take the log of that. Now we're going from negative infinity to 0. And if I wanted to look at what the graph of that looked like, it still has the same asymptote at x equals 0. However, my graph now goes through the point -1, 0, and does that. You don't have to graph them if it goes the opposite direction because this is negative. Remember, I can only take the log of a number where that number is greater than 0. Whatever's in that parentheses, 3 minus 2x, is greater than 0. And then I solve. If I add 2x to both sides, then I have 3 is greater than 2x. Then I can divide both sides by 2, and I cancel this, and I get 3/2 is greater than x, or x is less than 3/2. In interval notation, it would be from negative infinity to 3/2, and since it's less than, that would be an open parentheses. Thank you for watching.